Welcome to the lecture on solving exponential and logarithmic equations. The first type of exponential equation that we're going to talk about today are equations of the form b to the x equals b to the y. And that means that you're able to get the same base on the left side and the right side. If that's possible, then you can set the two exponents equal to each other. Not every problem can be made of this form, but when it can be, then it's usually a little bit simpler and easier to solve. So let's take a look at our first example. We have 64 to the x equals 16. You want to look at those two bases, 64 and 16. Right now they don't match, but it might be possible to rewrite them using a different base because these are both powers of 4. 16, as you know, is 4 squared. And 64 is 4 cubed. So I'm going to change both of these bases to their new bases, base 4. And when I do that on the left side, I want to use parentheses because this then becomes 4 to the third raised to the x. And this is a power to a power, so our laws of exponents tell us that we want to multiply. So 4 to the 3 raised to the x becomes 4 to the 3x. And the right side is 4 squared. Once the bases match, the only way that this equation can be true is if these two exponents match. So we set them equal to each other and we just solve for x. So in this problem, our solution is x equals 2/3. Okay, so let's try that on the next one. We have 9 to the 2x plus 1 equals 81. Is it possible to make these two bases be the same? And in this case it is, because we know that 81 is 9 squared. So now they both have a base of 9. So all we have to do is set the two exponents equal to each other and solve for x. So I'm going to subtract 1, divide by 2, and we get x equals 1/2. The next example has a fraction 1 over 27 equals to 3 to the 2x. Hopefully you recognize that 27 can be written with a base of 3 because 27 is 3 cubed. And because it's in the denominator, we can move this 3 cubed up to the numerator by just making that exponent become negative. So 1 over 27 is really the same as 3 to the negative 3. So it's possible to make both sides of this equation have base 3. So we can set our two exponents equal to each other, divide through by 2, and we get x equals -3/2. On the next example here, 32 to the 2x minus 3 equals 2. 32 is 2 to the 5th. So I can rewrite this as 2 to the 5th wrapped in parentheses, raised to the 2x minus 3. Now here's that power to a power again, so you want to multiply. And we really want to be using parentheses here and distribute that 5 across. So this becomes 2 to the 10x minus 15 equals 2. And when we go to set these two exponents equal to each other, what is the exponent over here on the right-hand side? It's an implied 1. So this becomes 10x minus 15 has to equal 1. So I can add 15 and get 10x equals 16. And then dividing by 10 and reducing, both 16 and 10 are divisible by 2, so we get 8/5. Okay? On the next example, we have another fraction again. Remember that when you have fractions, then you're probably going to be using negative exponents. So we know that 4 is 2 squared. And if I take that 2 squared and move it up to the top, then this becomes 2 to the -2 equals 2 to the 3x. The bases now match, so we set our two exponents equal to each other, divide through by 3, and we get x equals -2/3. In the last example here, we have 81 to the x minus 1 equals 27 to the 2x. Now we know that 81 is 9 squared. We did that in an earlier problem. But 27 is not 9 raised to a power. It's 9 times 3, but not 9 to the third. So it's not really useful here to use a base of 9 because I can't rewrite 27 using base 9. However, 27 is 3 cubed. We did that earlier. And 81 is 3 to the 4th. So we can make these bases match. We just have to use a slightly smaller base. So I'm going to change 81 to 3 to the 4th and change 27 to 3 cubed. And then we have power to a power, and we want to make sure we distribute. So when we distribute this 4 across, on the left side we get 3 to the 4x minus 4, and on the right side when I multiply I get 3 to the 6x. So now the bases match, so the exponents must be equal, so set them equal to each other. Let's get our x's together by subtracting 4x, and then we can just divide by 2, and negative 4 divided by 2 is negative 2. So all of these examples had something in common. You were able to get the left side base to be the same as the right side base. Once the bases match, then the exponents have to be equal. In the second set of exponential equation problems, it's not going to be possible to make the left side equal the right side. So if that's the case, then the only way to solve these problems is to use a logarithm to undo the base so that we can get at that exponent. So for example, if I have e to the 3x equals 5, there's no way to make e and 5 have a common base. So the only way to get at this x, which is up in the exponent, is to undo an exponential, and the function that undoes an exponential is a logarithm. Most of the time when we write our answers, we will probably want to know numerical values, and that means we want to be able to use our calculator. Since on your calculator the only logs with bases that we can use are log base 10 or log base e, which is an ln, those are the two kinds of logs that I would recommend using. In this particular example, since I have a base e here already, it makes sense to use a natural logarithm, which is also base e. So the very first thing I'm going to do here to get at this power is take an ln of both sides. So I'm going to take the ln of the left side and the ln of the right side. And as long as you're doing it to both sides, you're keeping the equation balanced. Now by choosing ln, which is a log base e, and taking the ln of e to the 3x, you guys should know that there is a cancellation property at work here. The ln base e and this base e cancel each other out, and all we get is this power 3x equals ln of 5. So to finish solving for x, all I have to do is divide by 3, so x is going to be ln of 5 divided by 3. To figure out what that is as a decimal, we're going to use our calculator, and you're just going to use your ln button, and we want ln of 5, close the parentheses, divide by 3, and giving 4 decimal places, rounding up here, I'm going to need 0.5365. So this is equivalent to 0.5365. If an instructor asks for an exact value, then you would leave your answer with ln still in it. If they ask for an approximation, then you're going to give the decimal value. Okay? In the next example, we have 5 to the 2x minus 6 equals 12. It is not possible to get these two bases to match. So to undo these exponentials, we're going to use logs. Remember, the best two choices to use are either log base 10, which is just a common log, or log base e, which is a natural log, an ln. You can do it either way. Since in the last problem I used an ln, this time I'll use a log base 10. So I'm going to take log of the left side equals log of the right side. Notice I'm not writing a base to this because it's an implied base 10. Anytime you see just log, that implies log base 10. Now this time, because this is a base 10 and my base of my exponential here is a 5, these do not match. So there is no cancellation on this side like there was in the last problem. So what I'm going to do is use my properties of logs, which say that if you have a power, like I do here, I can bring that out front, and I'm going to wrap that in parentheses. All of that power comes down as a coefficient in front of my log 5. So there's your properties of logs at work. And now to solve this for x, I can do a couple of things. I could either distribute the log across and then go from there, or I can just divide through by log of 5 right off the bat. And then I don't need these parentheses anymore because there's nothing that's going to be distributed on the left-hand side. So I would just have 2x minus 6 equals log 12 over log 5. To finish solving for x, I could add 6 to both sides. So I get 2x equals log 12 over log 5 plus 6. And then to finish dividing by 2, we want to divide everything by 2, so make sure when you divide, you're dividing the left side by 2, this fraction by 2, and this 6 by 2. And this is kind of a nice shortcut, just putting that 2 down there in the denominator. So these 2's cancel, and we just get log 12 over 2 log 5 plus 6 divided by 2 turns into a 3. So that would be your exact value. To get the numerical value, we just want to punch this in. So we're going to do log, just the log of 12, and then I want to divide this by both of these terms in the denominator, so you must use parentheses in your denominator. Parentheses 2 log 5, close the parentheses of the log and close the parentheses of your denominator, and then a plus 3 on the end. So this is about 3.7720 if I round off to 4 decimal places. So 3.7720. Okay, let's try the next one. E to the negative x plus 2 equals to 10. So we want to get at that exponent, and in order to do that, we need to undo this base e. And again, your two choices are to use log base 10 or log base e, which is an ln. And since I already have a base e, it makes sense to use an ln on both sides. So I'm going to take the ln of the left side equals to the ln of the right side. Ln of e cancels out to a 1, and all we're going to have left is this power. And then to solve this for x, I could subtract 2 to the other side. And then I need to divide through by a negative 1 or multiply through by a negative 1, which just changes these signs. So the ln of 10 becomes negative and the 2 becomes positive. You can leave it like that. Most likely your textbook would not lead off with a negative. They would switch this order around and write it as 2 minus ln 10. Either answer is correct. And then to get a numerical value for that, we're just going to substitute that in to our calculator. So 2 minus ln of 10 gives me negative 0.3026. And there are my two values. Okay. The last example here has exponents on both sides. So we're going to do exactly the same thing that we've been doing, but the algebra to solve for x here is going to be a little bit more complicated because we're going to have x's on both sides of the equation. Now here I have base 2 and base 5. I can't get those to match. And neither one of these bases is a base e. So you have your choice here of whether you want to do an ln or whether you want to do a log base 10. Both ways would be correct. Both ways will give you the same final decimal value. So again, I did ln in the last example. Let's do log base 10 on this one. So I'm going to take log base 10 of 2 to the 3x plus 1 equals log base 10 of 5 to the x minus 2. Because this is base 10, that base 10 does not cancel with the 2 or the 5. So there's no canceling out. But what I can do is use that power property for logs and bring this power out front, wrapping it in parentheses and multiplying it by that log 10, log base 10 of 2. We're going to do the same exact thing on the right side. Take this power, wrap it in parentheses, and bring it out front. Now in this case, again, you could do some division, but because we have x's on both sides, what I like to do is get rid of those parentheses first by just distributing my logs across. So 3x log of 2, you could just write it like that. There's no simplifying that you can do to that. And then 1 times log of 2 is going to stay log of 2. On the right side, we have x times log 5 minus 2 log 5. Now we have two x's here. We have this x and we have this x. We want to get them together. So I'm going to subtract x log 5 from both sides. And I'm going to squeeze that in between. So I'll have 3x log 2, and I'm going to squeeze in that minus x log 5. I still have this log 2 on the left side. And that log 2 right here does not have an x in it, so it needs to move over to the right-hand side. So I'm going to subtract it to the right-hand side. So I get my two x terms on the left and my two terms that don't have x's on the right. Now finally, because I have two x's and I need to simplify this down to a single x so that I can isolate it, the way to get these x's out is to factor it out. So we're factoring out x from both of these terms. So if I pull out x, then I'll still have the 3 and the log 2 left over from this first term, minus the x is gone, so I'll still have a log 5 left over. And then finally, once you've factored out x, you're almost done. All you need to do now is divide by the stuff in parentheses on both sides, and then we will have our final answer in the exact form. So x is going to be minus 2 log 5 minus log 2 all over 3 log 2 minus log 5. Now if you don't like having all those negatives in your answer, you could multiply the top by minus 1 and the bottom by minus 1, and that just switches all of the signs. So an equivalent answer would be positive 2 log 5 plus log 2 over negative 3 log 2 plus log 5. So either answer is correct, with the negatives or without. Now to type this in correctly, you are going to make sure that you need parentheses around the top and parentheses around the bottom. So let me show you how to type that in correctly. So we're going to have parentheses 2 log 5, close the parentheses for the log, plus log 2, close the parentheses for the log, close the parentheses for the numerator. Then we're going to divide that by parentheses negative 3 log 2, close the parentheses for the log, plus log 5, close the parentheses for the log, close the parentheses for the denominator. Hitting enter, we get negative 8.3234. So negative 8.3234, rounding off a little bit. Okay, so that's how we solve exponential equations. Either try to get the bases to match and then set the exponents equal to each other, or if the bases don't match, take either log base 10 or the ln of both sides and solve for x. To finish off today, we're going to talk about how you solve logarithmic equations, so the inverse type of problem. And in this case, what we're going to do is we're going to try to first get a single logarithm on one side of our equation, and we may have to use properties of logs to make that happen. And then once we have a single log, then we're going to undo the log by changing it back into its exponential form, and then we can solve that resulting equation. This is one type of problem where it's going to be very important that you spot check your solutions, because remember that you never want to take the log of a negative number, because that doesn't exist. So you want to make sure that whatever x or whatever your variable is, whatever you get for your solution, if you were to plug it back in, you never want to be taking the log of a negative number. So on this first example, I already have a single log, so we don't have to do any special tricks here. We already have our single log. So now all we have to do to get at this x is undo the log. So we're going to change this log equation into its equivalent exponential form. And remember, the way you do that is you take the base of your log and you raise it to the exponent that's over here on the right hand side, and that has to equal this argument, this stuff that you were taking the log of. So here's the equation that we get. 12x minus 8 has to equal 5 cubed. This is the exact same equation as our log equation, but this is written in exponential form and this was written in log form. However, this is easier for us to solve, so that's why we're changing it to exponential form. Now 5 cubed is something we can figure out. 5 cubed is 125. So now all we have to do here is solve this linear equation. I can add 8, and I get 12x equals 133. Dividing through by 12 gives me x equals 133 over 12, and that doesn't reduce. So we can just leave our answer like that. Now as a spot check, if you were to plug that back into this equation, then we would want to take log base 5 of 12 times 133 divided by 12 minus 8. These 12s are going to cancel out, so this is log base 5 of 133 minus 8, which is going to be log base 5 of 125. And that is a nice positive number, so we're taking the log of a positive, so that's why this is okay. So our final answer is 133 over 12. Okay? On the next example, we already have a single log, so we're ready to undo the log by changing this to an exponential equation. So I'm going to take 4 and raise it to the third power, and that has to equal this whole argument. So y minus 3 quantity squared. Now figure out what 4 cubed is next. 4 cubed, 4 times 4 times 4 is 64. And we get a little lucky on this one because we can use that square root property here to solve for y. The other option would be to FOIL all of this out, subtract 64 to get your 0, and then try to factor that quadratic. But as a shortcut here, we can just go ahead and take a square root of both sides right away. The square root and the square cancel out, giving you y minus 3. But on the right hand side, remember when you're the one taking the square root, you get two solutions, plus or minus, and the square root of 64 reduces to 8. So when we add 3 to the other side, we get y equals plus or minus 8 plus 3, and we can figure out what those two answers are. Positive 8 plus 3 would give me 11, and minus 8 plus 3 would give me negative 5. Now remember that you want to spot check those. So if I were to plug in 11, 11 minus 3 is 8, that's positive, so this is okay. Negative 5 minus 3 would be negative 8, which is seemingly bad. However, we get to square that. So when I do plug in negative 5 and get a negative 8, we square it and it turns positive, so this is doable just because of that square. So our two final answers are 11 and negative 5. Okay, the last few examples here have more than one log in the original equation. So this is where you need to use properties of logs to consolidate your two logs together into a single log first before you get to undo the log and write it as an exponential. So what property of logs can we apply here? If we have the ln of 3 plus the ln of x minus 1 equals to 0, there's a property of logs that says the ln of a plus the ln of b becomes the ln of a times b. So that's the property that we're using. Addition of logs becomes the product of their stuff, product of their arguments. So I can consolidate these into a single ln by just multiplying their stuff together. So 3 times that x minus 1. So I've taken these two ln's and made it into 1. If you want to go ahead and distribute that 3 across, you can. We get 3x minus 3. And now that we have a single log that's isolated, we're ready to undo the ln by writing this in exponential form. So the base of an ln is base e. So we take that base, we raise it to this exponent, so e to the 0, and that needs to equal this stuff inside the parentheses, so 3x minus 3. So there's your exponential form. e to the 0, or anything to the 0, is always 1. So we're just solving this linear equation. If I add 3, we get 3x equals to 4. Divide through by 3, and we get x is 4/3. Doing a quick spot check, if I plug x back in up here, 4/3 minus 1 is positive, so we'll be taking the ln of a positive number, which is what we want, so this is a valid solution. Okay, the next example is going to be done the same way because we have addition of these two logs. So addition of two logs becomes a single log, and we take the product of their stuff. So this x times all of this x minus 8. So use parentheses. If you want to go ahead and distribute that x across, we'll get x squared minus 8x. And once you have this single log, you undo it by writing it as an exponential. So 3 to the second has to equal all of this, x squared minus 8x. Figure out what 3 squared is. 3 squared is 9. This is now a quadratic equation, so to solve a quadratic you want to get a 0. So I'm going to subtract 9 over to the left-hand side. And most of the time, not always, but most of the time these will factor. So let's see if this one does. We need x's in the front. If I do 9 times 1 to get negative 9 and make the 9 negative and the 1 plus, negative 9 plus 1 gives me negative 8. So I do get the right factors. So my two solutions here, from this factor I'll get positive 9, and from this factor I'll get negative 1. Now here we want to do a spot check. If we plug in 9, this one would be the log of 9. That's good. We want to be taking the log of a positive. And here 9 minus 8 is also a positive 1, so 9 works. However, if I plug in negative 1, I'm supposed to be taking the log of negative 1, and that does not exist. That's not in the domain of log. So we are going to cancel that one out, and only 9 is our solution. Okay, in our last example, this time we have subtraction of two logs, and the property of logs that we're going to use at work here is that log of A minus log of B, when you're subtracting, that turns into division of their stuff. Not division of the two logs, but division of their arguments. So when I have log base 2 of x minus log base 2 of 3x plus 5, I can consolidate this into a single log base 2 with this x on top and this 3x plus 5 on the bottom. Notice again here that it's a single log. So to solve this, now that we have a single log, we're going to take 2 and raise it to the 4th, and that has to equal this whole big fraction. So let's figure out what 2 to the 4th is. 2 times 2 times 2 times 2 times 2 is 16. And now to solve this fractional equation, we can clear out this denominator by just multiplying the left side by the denominator and the right side by that denominator. On the left side, it just cancels out the denominator and we get x. On the right side, we are going to want to distribute that 16 across. So 16 times 3x is 48x, and 16 times 5 is 80. So this is a linear equation, so we want to get our x's together. So let me go ahead and subtract 48x to the left side. That'll give me negative 47x equals 80. And to finish solving for x, I just divide through by negative 47. And we get x equals negative 80 47ths. And then you want to do your spot check. If I take negative 80 47ths and I plug it back in for x, right away this one will not work because I'll be taking the log of a negative fraction, which is undefined. So this does not work. Since it was my only option as a possible solution and it didn't work, then my solutions would be no solution. Okay? Alright, that concludes our lecture on solving exponential and logarithmic equations. Good luck.